All right, so welcome to the second lecture, this lecture 1B on supervised learning and linear regression. So if you remember from last time, what we're looking at is at how machine learning broadly is divided in supervised learning, unsupervised learning, and reinforcement learning. We looked at a few applications, both in traditional machine learning or computer science, as well as how this would translate into chemical engineering. Now, what we're going to start with today is the actual technical content of the course, and we're going to start on the area of supervised learning, so building models, and of course we'll start with the simplest model, linear regression. Now, while linear regression might not be the most exciting of all models, it will set a good foundation for the next models to come, things like linear regression, Gaussian process decision trees, and so on. Okay, so this is what we'll be seeing for today. So before I start with linear regression, I want to talk about data pre-processing and particularly standardization. So you might have heard that in machine learning or in data science, a lot of the work comes from data pre-processing and just putting the data in the correct format. Now, in this course, we're going to be mostly focusing on the methods and the algorithms, so we're not going to look too much into it. However, standardization is a part of the pre-processing of the data that should always be done, and it's very important for just any machine learning model that is trained. And therefore, I want to spend a few minutes talking about this. Okay, so let's start with standardization. So this will also allow us to start getting used to the notation that we will be using throughout the course. So let's assume that we have collected 151 data points in 2 dimensions. So what do I mean by this? Well, remember that we had the example of the house prices where we wanted to predict the house price based on, let's say, number of windows and square meters. So number of windows and square meters are what we call our inputs, or our features, or our descriptors. And we can represent this by the matrix X. Now, this matrix X is made up of 151 data points. That means 151 house information that we have collected. And each of these data points at the same time, it's made up of 2 descriptors or 2 features or 2 inputs, depending how we want to call them. All of them are interchangeable. So let's assume that we look at the first house, which that's what I mean, the number 1, the first data point. And this data point comprises the number of windows for the first house and the square meters for the first house. Then we have a second data point here, which is a 2-dimensional data point because it's a house, and it has also its own number of windows and square meters, and so on and so forth, up to the house 151, which again is made up of 2 descriptors, which has the number of windows and the square meters. And we collect all of this data into what we call the matrix of inputs X. We have a similar matrix of outputs or vector of outputs with the house prices, but for now I'm going to focus on the matrix of inputs. So something that can happen with this matrix of inputs is that the different dimensions or descriptors vary widely. So let me now look at a chemical engineering example. So let's assume that maybe you're looking at a reactor and reactor conditions, and maybe this first column is the temperature of different set points. And the second column is maybe the pressure. So what can happen is that the temperature is going to be on the order of the 200s, while the pressure, actually depending on the units, but assume that it's in bar, then it's going to be in the order of, let's say, 1, 2, 3, depending on the reaction, but it's going to be, in general, much lower numbers than the 200s. And what that means is that your data might look like this, where one of the features, so this is, for example, the dimension x1, is very large because maybe this is on the order of 200s, and this other of the features, while there is some variation inside, we can't really see it because the variation is in much smaller numbers, again, the number of 1, 2, or 3 for the pressure. So we don't want that because then our machine learning models will have trouble retrieving the information with respect to this relative variation. And an even worse problem is that then your data looks different depending on the units that you're using. So if you're using bar, the data will look different than if you're using Pascal, or than if you're using atmospheres, or different units of your data. And again, this is something that we don't want. What we want is a data that looks like this, where all of the features are more or less in the same dimension. And this allows us to extract the information better. Now, to do this, what we do is we're going to pre-process our matrix of inputs. And what we're going to do is for every column, so for every feature, so let's say that these are the temperatures, I'm going to calculate the mean temperature. I'm going to call that mu1. And I'm going to calculate also the standard deviation of the temperatures. I'm going to call it sigma1. And I'm going to do the same. I'm going to calculate the mean pressure, which I'm going to call mu2. And I'm going to calculate the standard deviation of the pressures, which I'm going to call sigma2. And these are the typical equations. You know, the mean is just some kind of average, and then this is your typical expression for the standard deviation. Now, what I'm going to do now is I'm going to grab every single data point. So for example, I'm going to grab this data point, which is the temperature for the first operating conditions. And I'm going to subtract the mean of the temperatures and divide that by the standard deviation of the temperatures. And I'm going to put that point back here, this X bar. Then I'm going to grab the pressure for the first operating conditions, and I'm going to divide this X by the mean of the pressures and the standard. I'm going to subtract I'm going to use this equation. I'm going to subtract the mean of the pressures, and I'm going to divide by the standard deviations of the pressures. And that's going to be the number X2 upper script 1 bar, and I'm gonna substitute it here. And I'm gonna do that for every single data point of this matrix. Of course, I'm gonna do this in what we call the vectorized form, so I'm gonna do this quickly, so it's not very intensive. But what that means is I'm gonna end up with a new matrix, which is all standardized. And then here, that's what I'm representing. I'm gonna have then from this initial matrix of features, which again, these can be all in different dimensions and with relative variations that I don't want. By using this expression on every single data point, standardizing every data point by the mean of that feature and the standard deviation of that feature, I'm going to create a new matrix, X bar, where again, every single point is simply X bar. And this is basically going to be a standardized matrix. And this matrix is going to allow me to train my machine learning models much better by extracting our information. And yeah, basically from now on, I'm going to be assuming that I already have a standardized dataset. And this is going to become also much more clear when we talk about optimization of neural networks, which we'll see in a couple of lectures. But for now, again, the idea is that we want to transform our original dataset into a standardized datasets, which allow us to have the relative variation of the features in the same space, in the same relative variation, and that will allow our machine learning models to learn more appropriately. Okay, so let us now go actually into linear regression. So the idea of linear regression, we're going to start looking at it in the one-dimensional case. It's where, for example, you have inputs X and outputs Y, and you want to learn the mapping between them. So for example, again, if we're talking about predicting the prices of houses, then based on square meters, let's say, so the values of X would be your square meters, and the values of Y would be the prices of a house. And basically you collect, let's say 12, you go to 12 houses, you collect the square meters, which are X, and the values of the house prices Y. And then, for example, that means that, you know, for house number 6, you have the number of square meters and you have the price. Then again, for house number 12, you have the square meters and the price. And then the question is, okay, when you have a new house, you don't know the price, you want to predict the price of a house, you know the square meters of different houses. What are the approximate values of the house, of the price of the house? And this is what machine learning is about, right? It's about, based on input information, how to predict things that you don't know, but that you have learned from data. And this is what linear regression is about. So if your data is linear, then we can use something like linear regression to represent this quite well. So what happens with most machine learning models, or with many machine learning models, is that they will be defined by some parameters. So in this case, a line in one dimension is defined by two parameters, m, which is the slope, and b, which is the intercept where the line crosses the line of the x-axis, which is equal to 0. Now, focusing on this equation over here, what that means is that we can construct a model. So notice that this y has a hat. Generally, when I have a hat, it means that this is the model. It's not the true value. Now, I can create a linear model where given, for example, some square meters, so these are inputs x, because we can go to a house, measure the square meters, and then based on the parameters m and b, which we have learned from our data, we can give an approximate value for this value y. And this is the y hat, the model or the line of the prediction of prices. Now, a key question is that then we have these two parameters, m and b, which we want to learn from the data. So as we said, we want to collect lots of house prices, measure the square meters, and build a model that matches this data. And of course, there's many different lines that we can construct. And although maybe some of these lines obviously are not correct, it's important to have the best statistical line that best captures our data. And the way that we solve a problem is via optimization. So what we do is we pose this optimization problem, which what we're saying here is we want to minimize, so that's what the min says, the difference between our model. So notice that this is y hat, yeah, and our data d. Notice that we're minimizing because we're subtracting one from the other and we're taking the square. So we're minimizing the difference between the predictions of the model and the actual data y that we have. And we're doing that, we're minimizing this difference by moving around this m and b. So we're moving around the slope and the intercept such that we have the line that best passes through the points, minimizing this difference. So then the key idea is how do we determine these values, or how do we do this optimization? Well, it happens that this optimization problem, if I grab this function, it looks something like this, where I have the slope m and the intercept b. And notice how this is a bowl-shaped function of how the least squares, so here on the y-axis, here I have the least squares problem, how this changes with the slope m and the intercept b. And what I want to find is I want to find the optimal m, so this point here, the minimum of this curve, which would give me the slope m and the intercept b, that would minimize this objective function value over here. Now, this looks like a bowl-shaped function, and if you remember from your calculus classes, so let's assume that I'm going to look at the problem in one dimension now. Let's assume that we only have m here, and here we have our least squares. If we have a bowl-shaped function like this is what we call a convex function, and we want to find the minimum point here, what we're looking for is a place where the slope of this function is equal to 0. Because at the minimum, the slope of that function is equal to 0. And if you remember again from calculus, the way that we get the slopes is by the first derivative. So what we can do is we get the first derivative from this least squares function with respect to m. And we equate that to 0. And if we solve this equation, that will give us the m, the value m, that is this optimum point over here. Now, if we go to this 2D function over here, what we're actually doing is we want to do the same thing, but now we want to differentiate this function with respect to m and with respect to b. And that way we get two equations. The derivative of that function with respect to m, that's one equation. The derivative of that function with respect to b, that's a second equation. And then we have a system of two equations and two unknowns, m and b. And we solve it, and with that we find the optimal values of m and b that create the optimal line that passes through those points. Okay, let me now explain this with equations. So to make things a bit easier, let me redefine. So this expression, which is what we are going to be differentiating, I'm just going to rename it f_obj for f objective or objective function. This is just typical nomenclature that we use in optimization. And then what I'm going to do is I'm going to take the derivative of that expression with respect to m, and then the derivative of that expression with respect to b. Now here on the left-hand side, I put the derivation, but let me go through this. So again, first I take the derivative of this function, that function with respect to m, and this is this expression over here, and I equate it to 0. And I take the derivative of that same expression with respect to b, and this is this equation, and I equate both to 0. Now, I rewrite them just so that it's easier to see. So here I'm just rewriting the first expression, and here I am rewriting the second expression. And now here what you could do is simply, again, you have two equations. So this is equation 1 and equation 2, and you have two unknowns, m and b, m and b. And you can simply solve this system of two equations, two unknowns. If you want, you can even pause the video and try to do it yourself. I think it's useful to do it once. But anyway, so once you solve them, you should be getting something along the lines of what you can see here. So now I can get what we call a closed form expression. So it simply means that I have this optimal m and this optimal b. And notice that both of these are only functions of the data points. So I don't have anything else apart from the data points, which again, I've already collected previously. So I simply plug in the data points that I have, and I get my optimal m. Here I plug the data points as well, and I plug the m that I just computed, and I get also b. And these are the two parameters, so m and b, that define the optimal line that passes through the points, minimizing the square difference between the prediction and the data that I want to match. Now, I've massaged this expression a bit. In here, I haven't done anything else here. I've just simplified it because this is how you might see this expression in the literature. So these expressions for m and b are exactly equivalent to the ones in the previous slide. The only thing that I've done here is I have x bar, which is the average of x. So you know that would be 1 over 12 of the sum of my x i's. And that is that, and the same for y's. And this is just the way that we could define this closed form expression. Okay, so far so good. Now, if someone gives you a one-dimensional example, that means where you only have, for example, square meters. So when you only have one descriptor, you know how to get the optimal line that passes through your points. Okay, so now in this next section, what we're going to do is we're going to find linear regression. How do we find this optimal? Now, in this case, will be a plane when you have multiple inputs. So this is what we have seen so far, where we have a one-dimensional example where our features are only a scalar. So that means that we only have one feature, which is, in this case, in the example that we've been seeing, is the square meters. And now what I'm going to be denoting is ND for the number of data points. This is just the notation that I'm going to be following. What that means is that this is the first data point with the first house. So this is a 1 with this is the square meters and this is the price of this house. This is the square meters for the second house and the price for the second house, all the way to the ND house, where these are the square meters, and this is the price of the house number ND. And as we saw, we can simply build a line to find this optimal model to then predict the price of the next house based on the square meters. Now, what we're going to be seeing now is how we can use not only a single descriptor, but how we can use many of them. So now notice that the descriptors are a vector in nx dimensions. Again, that will allow us, and I'm looking at this part over here, that now I have for every house, I have the square meters, but maybe also have the number of windows. Maybe I have the postcode, which I'm able to encapsulate somehow, which we'll probably see in later parts of the course, all the way to nx descriptors. And notice that this I encapsulate as a vector. Again, similarly for ND data points or ND houses in this case. Now, what we will be seeing is that now instead of fitting a line, we will be fitting a plane or a hyperplane. So what I mean by this is that let's look at the two-dimensional example. So let's say that now we have square meters and number of windows. What we will be fitting is similarly the intercept B. So that would be the same as before. But now I will have one slope per dimension. So what that means is that I will have this slope M, I'm going to call 1. Maybe this is also the square meters. But then I'm going to have a second slope here, which I'm going to call M2, because this is the number of windows. And I'm going to have one slope per dimension of the input, or one slope per descriptor. Okay, so I parked this over here so that it gives me room to go through the description. So now, as I've said before, what I need to do is if I want to find my approximate model y hat, I need to find one parameter per each descriptor, plus the bias term that I had before. Now, in this context, as I mentioned before, this is the equivalent, or intuitively, this is like finding the slope for every descriptor that I have, plus the bias term. So here I've changed a bit of notation. Generally, I used to call this the intercept, and now I call it the bias. This is because in machine learning, generally we call this extra term the bias term, but I might use them interchangeably and they mean exactly the same. Okay, now I'm gonna do one other bit of change of notation. So generally in engineering or in chemistry or in physics, what we do is we denote these parameters with the tag theta. So this is what I'm saying here. So M1 is theta 1, M2 is theta 2, all the way to MNX is now theta NX. Now, the only thing that I am doing a bit differently is this B, the intercept or the bias. I am relabeling it as theta 0. That's all that I'm doing. So this is just a change of notation. And now what I do is I grab all of the parameters and put them into one parameter vector theta. And you can see this is theta 0 all the way to theta NX. Okay, so as I've said before, I've done nothing here. I've just done a change of notation just so that we can continue with the same notation throughout the rest of the lecture. Okay, and now what I need to do is exactly the same thing that I did for the one-dimensional example. So I am also minimizing with respect to theta. So what I'm moving around is these thetas, which are the slopes plus the bias term. And this is the model, y hat. And this is the data or the targets that I want to match. And again, I'm also minimizing the difference. Notice the minus there and the square. So I want to the same find the optimal parameters that minimize the difference between my model and my data. And this is exactly what I'm saying here, just more explicitly. Now, the way that we do this is exactly the same as we did it before. We simply take the derivative of the objective function, which in this case is this objective function, with respect to each of the parameters and equate that to 0. Now, it used to be that I had M and B, and then I had two equations and two unknowns. Now I have NX slopes plus the bias, so plus 1. So I have NX plus 1 parameters, NX plus 1 unknowns, which is my vector theta. And since I'm going to take the derivative with respect to each of them, I'm going to have NX plus 1 equations. This gives me a square system of NX plus 1 unknowns, NX plus 1 equations, and I can solve it exactly as I did before for the one-dimensional case. Now, the good news is that this also has an analytical solution. I'm going to take a bit longer to derive this time. I'm going to go through a few matrices and a few reformulations because I want to show you something that's called the normal equation, and it's quite an important concept in machine learning and just in general statistical learning. Okay, so again, just summarizing, I parked this part here, so I have a data set with multiple input nx. I'm currently using only one output y, and I have my vector of descriptors. As I said before, what I want to do is I want to minimize the difference between the model y hat and the data, and I do this by the same way as before, as taking the derivative with respect to each of the parameters, equating that to 0, and solving that system of equations. Now, I'm going to introduce a bit of notation. So this is the same expression that I had before, but now you see that I left a space here, and what I'm going to do basically is add a 1 over here. And basically what that means is that I am multiplying this theta 0 by a 1. So just as I have theta 1 and it's multiplied by x1, theta 2 and it's multiplied by x2, the only thing that I'm doing here is I'm grabbing a 1 and I am multiplying that by theta 0, which of course changes nothing about this equation. I just do it so that then I can do the following manipulations. So now I define the vector theta of parameters, then the vector y of outputs, and each of these, for example, is the price of a house. And then I define the matrix that I had before. These are the matrix of the features. But now this matrix is a bit different. I'm going to be adding this 1 as a column over here. And what that will allow me to do is to multiply this row over here, or each of these rows over here, by this vector of parameters, and basically give me this part over here. And this will allow me to have a nice reformulation that allows me to write this in closed form expression in a vectorized form. So again, just recapping, what I'm doing is I'm finding the solution to this optimization problem over here by taking the derivative, equating that to 0. And this has a nice analytical solution, which is this expression over here, where these x are these ones over here, including the 1 over here. This is what this column of 1s allows me to do. And the y is again this vector of outputs. Here t is the transpose and -1 is the inverse. And basically this is the closed form expression that basically I only need to have the data points y and x, which I have because this is the data points that I have collected, and it gives me the optimal parameters that fit the best plane or hyperplane to the data that I currently have. Now I've simply added this asterisk here. This is just the way that in optimization we like to denote optimal. So I'm just saying here that this parameter theta is the optimal parameters that again fit the plane. Now the nice thing is that now when I get a new observation, so let's say that I get a new house that I have the square meters and the number of windows and I want to predict the price. So first this I would denote x new. I simply add the 1, the bias, and then I directly multiply it by the optimal vectors of parameters. And what this will give me is the y estimated. I mean, I could put a hat here, but basically this gives me the best estimate that I can have given my data, assuming that I have a linear model. Okay, one other little nugget here is that here, so far we've used theta, and again, this is the typical convention in chemistry, physics, engineering for the parameters. When we move to neural networks, and we will move in a couple of lectures, these theta are basically going to be the weights. So when someone talks about weights of a neural network, they're not talking about anything else but some parameters that are tuned via optimization. But of course, we'll be looking at that in much more detail down the course. And now one last comment, but this more in the numerical side, is that when this matrix or our data points are too large, so let's say that you have in the order of 1 billion of data points, then computing this becomes quite challenging, particularly because you have here a matrix inversion, which you wouldn't really invert a matrix, you would actually solve it via some system of equations, which we'll be seeing later down the course. But the idea is that when your data points or your features are too many and your matrices become too large, then this starts to become intractable to solve in this form. And what you generally do is you solve them as we will be seeing with neural networks, where you have some iterative procedure to find the solution. But you're still solving the same optimization problem where you're trying to find the place where the slope is equal to 0. Okay, we'll be seeing much more of this when we go into neural networks. Okay, so in the last slide, we looked at the solution of this linear regression problem and via this expression over here. It so happens that this expression is called the normal equation, and let us briefly look at how actually we derive it, such that it doesn't seem like we just took it out of nowhere. So going back to our previous examples or previous slides, this is what we had. The only thing that I've done is now I've put this term over here. And the idea is that this is what I would call the vectorized form of this expression over here. And you can notice that I have the matrix X, so this matrix over here. And if I multiply, like in linear algebra, row by column, you would multiply this row of X by the column of theta, and you get this expression over here. Notice that again, that's why it's important to have the 1 here, the theta 0 here, and then minus the first element of y, which would be simply this expression over here, and again, you get this one. And then you get the norm squared, and that is how these two expressions are basically the same. Okay, so then how do we derive the solution or this normal equation? Well, we know that this norm 2 expression is the same as this one up here. You might remember from your calculus that the norm of a vector x, for example, the norm squared, this is equal to x transpose x. And this is the same thing that I am saying over here. Now what we can do is we can distribute the term. So this times this gives me this. This times this gives me that. And then this times this gives me this. And this times that gives me this over here. And then we notice that actually these two are actually scalars. And what we do is we can combine them into a single term. So now I have 2 times the original term over here. Then, just as we did with the one-dimensional example, this is our objective function. We know that this is basically a convex function. We want to find the optimum, and to do that, we get the derivative of the function, because we remember that the derivative is the slope. We want to find the place where the slope is equal to 0, which would give us that term over there. So therefore, we get the derivative of this expression over here. And again, by rules of differentiation in linear algebra terms, we know that this expression over here, we take out theta, but we need to add the 2 here. This is the same as saying x squared. We know the derivative of that is 2x. Then we get this term over here, and again, this term goes away because we're taking the derivatives with respect to theta, of course. So this whole term is a constant, and we get this term over here. And because this last term does not depend of theta, it just goes away. Now, what we need to do is to equate this equal to 0. Yeah, so that we find again the place where the slope is equal to 0, and that's where we find the optimal point. Okay, so again, I've just parked this here, equal to 0. The first thing that I do is simply pass this whole term to the other side. So that gives me this term over here, and of course the 2 just go away. And then I simply need to pass this term to the other side. So therefore, to take it away, I need to multiply it on the left by x transpose x inverse, so that I can take both away. And I need to multiply also the other side by the same term. That's why we end up here. And therefore, with this, we end up with the same expression that we said before. Now, one important aspect that I want to highlight is that if you remember, or if you go back to the equation of how we derive m, you can see that actually these two equations are very similar. So in the bottom here, we have the x squared term, which is the same as here. We have the inverse of that x squared term. Then we have here the x term, which is the same as this x term. And then we have the y term, which is the same as the y term. And actually, if you remember, we've always been saying that we are standardizing our data. So if you standardize the data, the mean is basically equal to 0. So then this goes away, This goes away and you're left practically with the same expression. Now, this happens even if you do not standardize your data, but if you're interested, you can derive it on your own and you see that the two expressions are equivalent. Okay, let us now move on to what we're doing in the case of multiple inputs and multiple outputs. Okay, so far we've seen what happens when you have one input, one output, what happens when you have multiple inputs, so multiple features, and one output. And now what we're going to see is what happens when you have multiple inputs and multiple outputs. So these are the exact equations that I had before. The main point here is that you might remember that we had x as a vector, so it means that you have nx features. Again, this can be square meters, number of windows, and so on. But so far, we've been saying that y is only a scalar. So it means that we're only predicting one thing, basically the price of a house. However, what happens when you want to predict more than one thing based on the same inputs? So maybe with the same inputs, you don't only need to predict the price of a house, but maybe you want to predict, I don't know, maybe how much it will cost in the future, or something else that is maybe not related to costs. But for example, in the case of chemical reactors, and I'm going to shift topics a bit, we've talked about that maybe if you have a reactor, you can input the temperature, the pressure, the operating conditions, and you can output maybe what's the concentration at the output. So what's the productivity of some chemical of interest. But you might also want to predict the selectivity, or other things that with the same inputs you can measure and you can match. And that is the idea here. How can we predict not only a single output, but multiple outputs? So now what I'm going to do is I'm going to change these equations to the ones with multiple outputs. And now these are how the equations look with multiple outputs. Notice that the only difference in this part, in this first part, is that y now is also in ny. So that means that each of these points is actually a vectors of outputs that we have collected. What this means is that now our optimization problem is not only summing over the number of data points, but you also need to sum over the number of outputs. So basically you have one of these sums per each output that you have. In this way, now this equation over here as well, this is exactly what I'm saying, this one, this hat, this y hat, basically it means that you're predicting or you're approximating every one of these outputs by one of these equations. So this is what I have, j for 1 to ny. Now, what this means also is that all of these equations are actually decoupled. And this is what we have when we have linear systems. For example, now our vector of parameters is a matrix of parameters, where each of these vectors, so this is the vector theta 0, this is one theta 0 per each output. So you have theta 0 for y1, theta 0 for y2. So if you're predicting different things, you have theta 0 for the selectivity, theta 0 for the productivity, and so on. So that's why you have a whole, each of these is a vectors, and then this ends up being a matrix. Now, our matrix X is exactly the same as we had before. This has not changed at all. And the last thing that has changed is this Y. And now basically, again, as I said, for example, Y1, which is your first, let's say, house, or your first operating conditions of a reactor, now you have many things that you want to predict. So in the case of a house, we said that you want to predict the price of the house, but maybe you want to predict other things. In the case of the reactor, you might want to predict the productivity, but maybe also other things like the selectivity and so on. So now each of these data points is a vector. And the solution is also exactly the same. So this part is exactly the same, but now we simply have this matrix over here. So everything that we had before, how you derive this from the normal equation and everything stays the same. And also again, once that you have a new, let's say, a new number of windows, a new square meters, you simply add the 1 as before, and then multiply that by this matrix of parameters. And you will see that the dimensions will match, and you will be able to multiply them, and that gives you the new, now it's not a single estimate, now it's a vector of estimates, again, of all of the things that you want to predict. Okay. Now what we're going to do is we're going to look at some code of how this actually looks when we put this into some computer code in Python. Okay, So now what we're going to do is we're going to see how the equations that we saw throughout the lecture actually match what we implement in code and how this code then can fit some data sets that we're going to be looking at. So as you remember, to fit using linear regression, we need the matrices X and the vector or matrix Y. And these are the two things that I'm representing here. Now this is the values for X, and these two are the different values for Y, because I have two different functions that I'm going to try to fit. You can see that, for example, for the values of X, we have here a -12, and this is the coordinate X for the first data point. Then you can see that I have a -10. Again, this is the coordinate X for the second data point, and so on. And then I have two different functions Y that I want to fit. I have this function, so these values over here, and these come from a sum of a sign and a squared variable. So this is what I say, you can read it here. Then for this other data set, basically the values come from a sum of three different Gaussians with different means and standard deviations. We're going to see how this is fitted, but later we'll see what shapes actually, or how they look like. Okay, so this is the Python code that we've written. It's important to mention that this Python code is not meant necessarily to be general or to be for performance. The idea here is that I wanted to go through the steps to be able to very clearly explain what's happening. So we assume as inputs to the linear regression code, as we would expect, is our matrix of data X and our matrix of data Y. So this is what I've represented here, just so that you can have it in your mind. Now, the first thing that we do, I kind of showed it here, but it's basically that we kind of retrieve how many data points we have. We can do this from our matrix X. You could also do it from Y as well. Here I decided to do it from X. And then the first thing that we do is we add the bias column. We do this by using np.ones, which will simply give us a column of ones of some dimension, in this case, the number of data points, and we add that to the matrix X. And this gives us the matrix X with the addition of the bias, as we saw during the lecture. Then with the matrix X and our inputs Y, we can already compute the optimal parameter values. We remember that we used the normal equation for this. A couple of comments here. We use at as a matrix multiplication. This is a shorthand of NumPy, so you can see that we're using it in several places here, here, and here. And we use also a diagonal np.I to give us a diagonal matrix. Now, while you could compute this directly, here I just split it into parts just so that it can be better visualized. So first I computed X transpose X, so it's here. Then I computed X transpose Y, which is here. And particularly here I've added also some extra bit that I didn't talk about during the previous lecture, which is that I added this diagonal matrix, this one here, plus a very small value. And this is just to help us numerically to be able to necessarily invert the matrix. So you might remember that this X transpose X needs to be full rank. This is not going to happen if, depending on the noise level of my measurement data of my data points, but what can happen is that if I measure in exactly the same place twice or very close together because numerical error, my matrix might not be invertible. So because of that, we add that little very small number to try to not really bias basically the estimation, and plus a diagonal matrix. What that is equivalent to is to each of the values of the rows, we're adding a very small perturbation. Again, this is just for numerical stability. Yes, and then with this, we've already calculated basically the optimal thetas, again, exactly as we did during the lecture, using exactly the same equations. And then what I do is give it a new observation. So this I do at initialization. The way I coded this is, as soon as you initialize this model, you give it the parameter X and Y, sorry, the data points X and Y, and then you create the optimal theta, which is then saved inside the model. And then anytime that a new data point comes in, so here I just denoted X new, we add the bias term, and then we directly simply multiply then that new x new with the bias term times the optimal thetas that we've calculated before. And that is that line below there that you can see. Okay, so how does this look like? So we've taken this x and y and we've done it twice, one for each of the functions. And we see that, of course, we're fitting a line to something that is definitely not aligned. So this works as long as our data is linear. However, what we can do is look at something called general linear regression. And this is going to be the last thing that we're going to be seeing today. So far what we've done is we've said our output is a linear combination of our input. Again, this is what we say with linear regression. So we're saying the price of a house is a linear combination of the number of windows, the postcode, the square meters, and so on. However, what might happen is we might say, well, actually, I know that the price of a house is quadratic with respect to the number of windows. Or maybe it's a multiplication of the number of windows times the square meters. And therefore, we could do something more along the lines of saying, well, I know that this is the price of the house, y, and maybe my features, x, are quadratic. And therefore, what we can do is we can pre-process the data and multiply, for example, the number of windows squared. I assume that that is a new feature. Maybe the number of windows times the square meters. I assume that that is also a new feature, and so on and so forth. And what I could do then is I could fit the price of a house to then this quadratic combination of the features. Now notice very importantly here that the parameters are still linear. So this is still a linear combination of the parameters, but they multiply nonlinear combinations or nonlinear functions of the features. Now, we don't only need to do this for quadratic terms. We could actually have any kind of function here. And this is what we will call the basis functions. So we could decide that, again, maybe it's a linear quadratic combination of the features. We could say maybe the features are sines or exponentials or logarithms or strange multiplications or of combinations of the different functions. As long as these nonlinear transformations, which again we call the basis, are only of the features or only of the inputs, and our parameters still appear linear, we can still do practically linear regression. And that's what I'm going to show next. Okay, so we start similar to our pure linear regression example, where we have the input matrices x, and in this case, the vector y. And this new function is called basis f regression. And again, it takes the inputs x and y. The first thing that it does, similarly as before, it extracts all the number of data points. And then what we're doing here is we are non-linearly manipulating this matrix X. So notice that we only do it for the input features or this matrix X. So we add a quadratic term, we get a cubic term, we add a sine, we have a cosine. We of course add the bias, as we always should. And then what we do here is we combine all of them together into a basis vector. And notice that now here, while the outputs y remain the same, this is the same vector that I had before, the matrix X is now slightly different. So to be a bit more explicit, what the matrix X used to be was just this part, where it used to include the bias term, which we always include, plus all the features. In this case, we assume that we only have one feature, for example. But now what we're doing is we're grabbing also that same feature. Let's assume that, again, this is maybe number of windows. And we get number of windows squared, number of windows cubed, sine of number of windows, cosine of number of windows for the first data point. So for the number of windows of the first house. And then we do that also for the second house and so on and so forth, all the way to the ND number of data points, or just for all the houses. And notice that this is equivalent. So in this example that I'm showing here, we only had one feature. I can assume number of windows. And now we're saying as equivalently as if we had more features. We just basically creating these nonlinear relationships. And this is what this is called the basis vector. And then what we do is exactly what we did before. We simply grab now this is our new matrix X, which I called matrix XBF for basis functions. And we simply do the same thing. We basically compute the normal equation. This is the exact normal equation as before. I do it just as before again. I first do the X transpose X, then the X transpose Y, then I do the inverse, and I add this little nugget so that it's easily invertible. Just to be clear, I didn't mention it last time, but this you definitely don't have to do. I do it here just so that it's more understandable, but you definitely don't have to do that. And then the inference is exactly the same as before. The only thing is every time that you get a new data point, you need to add for example, if you get a new number of windows, you need to add the bias as you would before, but then you would also need to put number of windows squared, cube, sine over windows, cosine over windows, and so on and so forth. I noticed that here, having sine and cosine of number of windows, and since it's integer, it's a bit silly, but you get the big picture idea. Okay, so let's try this approach on the example that we had before. So you've noticed that now I changed this to XBF for X basis function. And now this is basically what we call the basis set. So it includes the bias that we always had, the typical feature, and it includes the expressions that we had before, X squared, X cubed, sine of X, cosine of X. Now, when we actually apply the procedure that we talked about before, this is what happens. And there's a few interesting things here. So the first thing is that this function fit perfectly. And the reason behind this is that the function that produced this data is this sine of X plus 25 of X squared. And you notice that both of those expressions are here. So one of them is sine of X, the other one is X squared. And remember that linear regression finds the global optimum because this is a convex problem. So that means that we're able to find the optimal combination of these basis functions. And the linear regression is basically able to find that X squared is actually multiplied by 25. That is the value of the theta that multiplies X squared. And that the value of sine of X is actually theta is equal to 1. And therefore we're able to fit this function perfectly. Now I'm cheating a bit here because I don't have any noise. And I did this again for illustration purposes, just so that we can see that the fit is perfect. If you have noise, the fit will definitely not be perfect, and you might have other functions in there. So here, the function that was estimated was exactly 25x squared plus sine of x. But if you have noise, you might have, maybe 0.01 of cosine of x and 0.03 of x cubed. You might have this small parts of these functions, other functions that are slipped in. There are procedures to deal with this. We're going to talk about that more in subsequent parts of the lecture, actually in the next lecture about machine learning models. But for now, this is what you need to know. Now, on the other hand, this function over here, as you might remember, I said that this is the sum of the three Gaussians, and you can see that this is one Gaussian, this is the other Gaussian, and this is the other Gaussian. All of them with different means and different standard deviations. Now, here the fit is terrible. It's maybe even worse than linear because it explodes here and maybe here. But the point here is that this is a bad fit. Now, the important things to highlight here: one, even if your functions that produce the data are not in your basis set, that doesn't mean that the fit is going to be terrible. In this case, it is, and that's what I wanted to highlight. But in many cases, it might be good. In many cases, depending, of how, on a case-by-case basis, depending on how close the real function is to your basis set, you might get some good behavior, and you might even be able to have some good extrapolation capabilities. But this goes more in a case-by-case scenario. But the idea here, and what I want to highlight, is that if you have some idea of what your function looks like, this general linear regression might be a good idea, because you can really it's almost like a way to inject knowledge into the machine learning model, but the machine learning model will select on its own which are the best or the most likely functions that produced the data that you want. Okay, so that ends the lecture for today. So just as a brief summary, today we were looking at linear regression, which is, we can think of it as a supervised learning model of machine learning. And we did that by looking at the data set that we would get, and that we're basically estimating a line, a plane, or a hyperplane, depending on how many inputs we had, and that we generally did that by estimating the bias and the different slopes. We said that we estimated this model, or we constructed this model, by solving an optimization problem. And this is basically what we will be doing for practically every machine learning model that we'll be doing, where we try to minimize the difference between the model and the data. Now, we saw that in the case of linear regression, predicting is very easy. We simply grab the optimal parameters, we multiply it by the new inputs that we just got. So for example, in the case of a house, again, number of windows, square meters, and that would give us the prediction that we wanted. Finally, we saw that we could use linear regression, or more what we call general linear regression, to do fittings of nonlinear functions, particularly when the features were being nonlinearly combined in some way, but that we still needed to have the parameters in their same linear form so that we could do the same procedure. And we did this still by minimizing the difference between the model and the data in the same way. Okay, so in the next lecture, what we'll be looking at is different machine learning models. So what I'll do is I'll relatively briefly walk through things like, I'll talk a bit more about generalized linear regression, particularly on this automated selection of features, or some of the ways that people have done it. I'll also talk about decision trees, and I'll touch relatively briefly on things like Gaussian processes and neural networks. This is because after that, I'm going to be doing a deep dive on neural networks, because they're a very important machine learning model, and also on Gaussian processes. I might have a few optional videos on the way, things like maximum likelihood estimation, things that you don't necessarily need to watch to keep with the rest of the content, but something that might be interesting for people who want to learn more about this topic.